Good afternoon. I'm Polly Puller, and I'd like to welcome you to Wigton Book Festival's exciting Big Bang Week. I'd like to start by thanking the funders for Big Bang, the Batchworth Trust and Killigalleoch Community Fund. Books discussed throughout Big Bang are available at the Festival Company online bookshop at bookshop.wigtonbookfestival.com. And questions for today's speaker can either be put in the comments field of the YouTube event or by pressing the question button below the event in the festival website, www.wigtonbookfestival.com. And I will be asking a selection of these as we go along. I'm absolutely delighted to introduce Dr. Nathan Case today, who is a space physicist studying the interaction between the solar wind and Earth's magnetic field, known as the Magnetosphere. He earned his PhD in space physics at Lancaster University before moving to NASA Goddard to work on the AuroraWatch citizen science project, collecting observations of the aurora. He then came back to Lancaster to continue his research, and he's specifically interested in how the interlinked solar wind magnetosphere ionosphere system evolves over time. He's a keen science communicator and frequently runs outreach activities and appears in the media on aurora and space-related topics. He's also one of the team running AuroraWatch UK. Nathan will start now by giving us a short talk on space, weather, and the aurora, the fabulous and mysterious northern lights, before we have a chat. And then hopefully, if time allows, he'll be able to answer questions. Good evening and a very warm welcome, Nathan. And thank you so much for joining us.
Thank you, Polly. It's my pleasure. You're going to give us a talk now. For sure, yeah. So thank you very much for this opportunity. And tonight's talk, as Polly's just said, is going to be about the northern lights, or the aurora borealis. And it's a really exciting topic, and I hope that you'll learn quite a bit as we go through. I'm sure plenty of you who will already be quite well versed in the aurora and the northern lights, you might have actually seen the aurora on multiple occasions here in the UK. So if we could have our first picture up, then we're looking at the aurora. This is the aurora from Iceland. It was captured a few years ago. And what we can see here is this magnificent light display in the night sky. And the aurora has captured our imaginations for centuries, if not millennia, as this phenomenon that occurs. And it's just an absolute draw for people into understanding the modern world and understanding the world around us. And of course, my research is now using state-of-the-art satellites and ground-based instruments to really understand the science behind the aurora. But you can imagine that centuries ago, when people were seeing this phenomenon in the night sky, they had absolutely no idea what was going on. And an event of this magnitude of bright colors dazzling across the whole sky really captured the imagination of these prehistoric civilizations. And it's really nice to look at sort of the mythology behind the aurora and to see how it affected the beliefs and the stories that were being told by these different historical societies. For example, with the ancient Romans and ancient Greeks, who were obviously based in the Mediterranean region, they very rarely saw the aurora. But when they did, it would be a phenomenal event, often quite red in color, unlike this lovely green that we can see in this photo. And that red actually produced some ominous fear in the population, and they would often associate that this event must be that the gods were trying to show their displeasure with society. But for other civilizations who saw the aurora perhaps more frequently, the associations were better, they were good. One of my favorite ones is about the Finnish society, and they would associate the aurora being the flaming tail of a firefox racing across the night sky. I think that's a beautiful image to capture. And with the Viking civilization, there's some debate about how often the Vikings might have seen the aurora and what they associated with. I think the Vikings weren't particularly well known for writing books or writing things down, but it's often been presumed that the aurora have been associated with the Bifrost Bridge, the bridge from which fallen warriors would travel to Valhalla, their final resting place. And I think that's a beautiful imagery to capture as well. So this talk is just going to run you through a bit about the aurora, how it's formed, and the science behind it. And I'll try and keep it light so we're not diving too much into the physics exactly. And then, as Polly said, we can have a few questions about what's going on. So if we click through into the video, this is just a short clip of the aurora, and we'll play it a couple of times. And what you can see here is that the aurora forms these arcs, which are called auroral arcs, and they're this green bending of the light through the night sky. But also we have these bright patches that appear and disappear over time, and it really shows how active and dynamic the aurora can be. So we've had a little preview there of what causes it, but the aurora themselves are very ethereal in how we see them. You can see how the starlight is actually shining through the aurora. And so when you see these by eye, sometimes you'll be able to pick out the color, but sometimes it might look more like a mist that's sort of dancing in the night sky. And it's really important actually to think that when you're looking for the aurora, which we'll come on to in a bit as well, that you need these clear night skies to be able to see it, because any light pollution will wash out the aurora, and any clouds in the sky will actually hide the aurora too. So nice crisp winter evenings, winter nights are brilliant for aurora hunting, especially if you're at higher latitudes. So how did the aurora form? What's the driving point and the mechanism behind them? Well, to know that, we have to look 93 million miles away and look to the sun. And we can skip to the sun's picture now. The sun itself is a constant in our lives, obviously. We generally see it every day, although here in Lancaster, quite often we don't see it for days on end. But it's there, it's providing the warmth and the light that we need to survive here on Earth. And it is the life giver in general. It provides that energy and that warmth and that we need for life to live on Earth. The sun is a ginormous ball of plasma, and plasma is a really heated and excited form of gas. So it's so hot that electrons are ripped off from their atoms, and it's the fourth state of matter known as plasma. It really is ginormous. If you took everything else in the solar system, so if you took all of the planets and the moons and the asteroids and the comets and all of the other little space debris and rocks in the solar system, and you squished them all into one ball, that ball would only be 0.1% of the mass of the solar system. The other 99.9% of the mass in the solar system is made up in the sun. So it is this huge ball of plasma. And in fact, it's acting like a power plant. It's a nuclear reactor. The pressures inside the sun are so great that hydrogen atoms are smashed together to produce helium. And when that happens, energy is given off. And it's that energy which is given out into the whole solar system and spreading out right until the far reaches, even out to Pluto and beyond. When we look at the sun and we kind of think it's quite constant, but it's not. It's very dynamic. There's lots of things going on the surface, and its activity actually waxes and wanes over time in what we call the solar cycle. So at times it's very active at a solar maximum, and then at times the activity drops off to a solar minimum. And in fact, we're just coming out of a solar minimum now. The sun's kind of waking up from a bit of a sleep. And what we can see on this photo is a solar filament. And that's that structure on the left bottom side there, kind of at about 8 o'clock on a clock's face. And that solar filament is this big structure coming off the surface of the sun. And it's going to release a huge amount of energy into the solar system. And we've got a video here from some NASA spacecraft, and actually recorded this happening from multiple different angles. So if we can click through to the video. So what we'll see in a second is the sun again at the same time, and you'll see this filament that's coming off the sun here, this big loop of plasma, And you can see that it extends really far out into space and then explodes. So this plasma loop breaks apart and throws out a whole ton, or actually millions of tons of solar particles and solar mass out into the solar system. And we're talking millions of tons of plasma and millions of joules of energy here. It's a very large event, and it's releasing that energy out into space. Other things we can see here, we can see lots of dynamics. We can see magnetic fields and plasma bubbling away on the surface of the sun, which we call the corona. And we'll see this filament explode from a few different angles here, but you can also see other things going on as well. You can see this kind of fuzziness around the edge of the sun, which is constantly blowing off plasma from the surface, and we call that the solar wind. So here's another view from another spacecraft a little further away, and again we can just now kind of appreciate the size of these coronal mass ejections, these explosions off the surface of the sun. And again here now, so we can see this going off in a large direction and heading towards us as the viewer is this coronal mass ejection. And now we've got a really nice situation where we can actually see this from the back of the sun as well. So we're facing the sun from the other side, but now we've got a spacecraft behind the sun, and we can see this coronal mass ejection, this explosion of energy coming off the surface of the sun. And so as we know now that the sun is active and it can have these coronal mass ejections, it can be forcing this energy off. We can kind of think of that as there's a background solar wind, and that's kind of like a summer's breeze. It's always there. It's the gentle background level of wind that's coming off the sun. But then at times the wind speed can increase, and it can be faster and gustier. And at times it can really explode off, so these CMEs, and that's kind of like thinking like a hurricane. And I just wanted to show here the actual scale of what we're talking about, this filament and then this CME that explodes off. We've got the Earth to scale next to the filament. Of course, the Earth isn't really this close to the sun. If it were, then we'd all be burnt to a crisp. So we've moved the Earth much closer to the sun, but kept the scale the same. And so you can just now visualize how much energy is being released from this explosive event, and just what that would mean to us on Earth if we didn't have anything to protect us from it. So if we skip through now to the next picture, what we can see here is a diagram. It's a drawing. This obviously isn't a real picture, of the sun on the left, and then of this coronal mass ejection, this explosion of energy coming through space in the middle. And then on the right, we've got Earth, that blue marble that we're all familiar with. And then surrounding us is the Earth's magnetic field. And we call that the magnetosphere, as Polly mentioned earlier. And this is where my research is focused on, is Earth's magnetosphere. So if we click through to the next picture, we zoom in a bit on the Earth. And what we can kind of see now, if you can recall back to your science lessons where you've maybe had a bar magnet and you can drop some iron filings on the bar magnet, and you can see that the bar magnet will produce a magnetic field, and it looks very similar to this. And that's because the Earth is kind of similar to a bar magnet. It has a north and a south pole, and it has this magnetic field that surrounds us. But it's a little bit different from a bar magnet, because we've got this solar wind constantly streaming off the sun, colliding and crashing into our magnetic field. And so that squishes the day side of the Earth, so the side that's facing the sun. It squishes the magnetic field, and then it stretches it out on the night side, to the side facing away from the sun. And so we kind of get this like comet tail shape where the magnetic field is being squished and stretched on the other side. And this is our magnetosphere. It's our magnetic bubble, our shield against the solar wind and against all the energy that's coming from the sun. But it's not perfect. In fact, when conditions are right, energy from the sun and the solar wind can actually enter into our magnetosphere. And studying that is kind of the effects of space weather, which you may have heard of. And space weather is a really important field for us, especially in today's technological society. Because things like satellites, communication grids, even power grids are susceptible to space weather. When we get really large coronal mass ejections, when they come colliding into the Earth's magnetic field, and when the orientation of the magnetic field in the CME is the opposite to the Earth's magnetic field, we get an exchange of energy. And solar flares and streams of high-speed particles can come colliding in Earth, and they can destroy satellites. They can generate induced currents in power grids. They can even interfere with railway travel, because if you can imagine, obviously on railway tracks you have the actual railway lines themselves. They're big, long conductors, and if you generate electrical currents in those conductors, it can play all sorts of havoc with the switches and relays, and it can cause rail networks to shut down too. And so it's a really important field of study. But the impact of space weather that we're really interested in tonight is the aurora and the northern lights. So if we click through the next animation, what we can see is when some of these particles enter into the magnetosphere, they get trapped on the magnetic field lines in the magnetosphere. And then they can get accelerated down from outer space into our atmosphere. And that's kind of what we're seeing here. So these particles are trapped on these blue field lines, and through a process called magnetic reconnection, they get accelerated down into our atmosphere, and they create these crowns of glowing aurora around the magnetic poles. And so this is particularly why we see the aurora in the high latitude regions, so places like Scandinavia, Iceland, and Canada. But we also sometimes see them from the UK or places such as New Zealand and Australia too. So when we think of this, we accelerate these particles that have come from the sun. They've traveled all the way through space from the sun to the Earth. They enter into our magnetosphere, our magnetic bubble. They've managed to break through the barrier into our magnetic bubble, and then they get accelerated down into the atmosphere. And when they're there, a bit of science happens, and this is what the next slide will show, is that the energy levels inside the atmospheric gases becomes really important. So this is a bit of science. So for those of you who've maybe done physics or chemistry, you might know a bit about energy levels. But for those of you who don't, I'll try to explain this in a bit of a different way. But we can think of this as particles coming through down into our atmosphere, and they collide with the atmospheric gases. So the molecules that make up oxygen and nitrogen, the airs that we breathe, they bump into those atoms and those molecules, and they give them energy. So if I was pre-COVID times, if you and I were walking down the street and I bumped into you, I'd transfer some energy from me to you, and that might cause you to stumble or trip or something like that. And that's because of the energy I've given you. And when atmospheric gases get this extra energy, they don't really like it. They want to get rid of it. And the way they do that is giving off light. So another analogy here is if you imagine giving sugar or sweets to children, you're giving them energy, and then they become hyperactive and they become playful and they're mischievous and start causing mayhem. Well, that's them releasing that energy. And then after that's happened, they might suddenly crash and fall asleep or something like that. And that's them returning to their ground state, their lowest energy level. And so we can think of that the same as these atmospheric gases. They're given some energy. They then try and get rid of that energy, but instead of burning it off by running around like the kids would, they instead give off light, because light is a package, like a small parcel of energy, essentially. So we think of light as what we can see, but it is also like a packet of energy. And so the actual atoms can give that off to reduce their energy level. And they can do that several times, so they can give off different photons, different wavelengths of light to release the energy that they've received from the incoming particles. Now, when this happens on a really large scale, so when you've got an immense amount of particles and energy coming in to our magnetosphere, and they get accelerated inside our magnetosphere and channeled down and funneled and accelerated down into our atmosphere, when that happens on a large enough scale and you excite enough atoms and molecules in the atmosphere and they start giving off light, that's when we get the aurora. So the aurora is actually this end result of a whole chain of reactions that have gone on, starting from 93 million miles away at the sun. And I think sometimes we're very used to seeing the aurora from the ground up. We see these photos, or if we're lucky enough to see it ourselves, we're looking from the ground up to the aurora. But I think this next video is really neat because it shows the aurora looking down. This video was captured from the ISS, the International Space Station, as it orbits around the Earth. And from this perspective, we're actually looking down on the aurora. So we can see the ground there with the city lights. And then we're seeing this auroral band, this green light really shimmering away in the night sky. And we'll go through this clip a couple of times and we'll point a few things out. But it's really nice to see this perspective of the Earth. And now, as the ISS is moving across, and we can see the solar panel coming across the view, and it's starting to be morning now with the light coming there from the sun. So if we can go back. That's it. What we can see is that there's structure to the aurora, this height there. So we can see the atmosphere, this golden glow in the top left. And then we can see the aurora is going from this green base layer, reaching up with different spikes and pillars, and they're going up to this red color. And then we can see flashes of light. We can see arcs that are moving back and forward. And this is all due to the dynamics of the aurora and the system that's going on in this near-Earth space. And the different structure is what gives the aurora different colors. And we'll perhaps come on to that in a minute as well. Let's go through it one more time. I think it's a lovely video to see. And you can see that this aurora, it's confined in a specific region, and that's around the magnetic poles, because that's where these energetic particles are coming in. But that it's in that region, you can see lots of fine scale structures too. And that's what scientists are analyzing. They use spacecraft observations as well as pictures of the aurora to actually undertake science to help us understand more. Hopefully that was a quick tour through the aurora, and you can, we've got a bit of information now about what causes the aurora. You know now that the sun is this driving force behind it, and really this whole chain of interactions from the sun through to interplanetary space around our magnetic field, and then drives down into our atmosphere, causes this beautiful phenomenon that we know as the northern and southern lights.
Absolutely fascinating. I've got a question straight away. What causes extraordinary colors?
It's beautiful, isn't it, that we can see so many different colors coming out from the atmosphere. So as I mentioned about the energy levels, so as the particles that are in the sun, in the atmosphere, the atmospheric molecules such as oxygen and nitrogen, they get excited and they give off that energy in the form of light. Well, the complex chemistry that goes on there, it means that there are different energy levels in these atoms and in these molecules, and those different energy levels have different sort of gaps between them, and it's the size of that gap that will cause the color of light to be given off. So it's a mix of the different molecules in our air. So atomic oxygen gives off the really green that we're used to seeing with the aurora, but at high altitudes, so at the tops of those spikes that we saw in the ISS video, it gives off the red color that we can see. And then nitrogen tends to give off like a blue color, and that can make the aurora seem a bit purple, or even during strong events, it can actually give off a pink color as well. So if it's a really strong CME, for example, that coronal mass ejection explosion from the sun, then we can get some pinks in there too. And then these colors sort of intermix as well, and so we can get beautiful displays of all different colors.
So does it depend on where you are? I mean, would we ever see such vibrant colors in the north of Scotland, or do you need to go even further north to see those?
If we're lucky, you can, yeah. During strong events, then we can certainly see like these pinks come through on the base of the aurora, so at low altitudes, and then we'll see these greens predominantly. But for sure, as you go to higher latitudes, so you go up to, say, Iceland or Scandinavia, then you generally see these stronger events, just because you're in a better position to see them. And we'll quite often from the UK, and particularly Scotland, you'll see like the green bands on the horizon. But sometimes still you can get aurora going overhead if it's a particularly strong display, and you can pick out those colors too.
Is a sound ever associated with the aurora?
Some people have said they can hear a sound with the aurora. I think the general consensus is that we don't really know. We certainly couldn't explain any sound. And so it's an area of research that I think is going on. It seems that our understanding of the physical processes behind the aurora shouldn't result in any sound, but that people have reported it. So it's something that's being looked at.
When were they first recognized and understood for what they are, rather than being viewed as ethereal, otherworldly events? I mean, at what era in time was that sort of recognized officially?
It really wasn't that long ago. So the first observations of the sun's activity, of sunspots, were only a few hundred years old, and people were starting to look at through telescopes to look at the sun, which obviously don't do that. Don't look unaided at the sun. And so people then started making that link between things that were happening on the sun and the aurora, and seeing, oh, maybe these two things are tied together. And then it wasn't really until the space age that we started to be able to actually take measurements of what was going on in space to understand how those processes were really linked together. But it's certainly been thousands of years that we've been documenting this. There are petroglyphs, cave drawings of the aurora seen in Australia by the Aboriginal cultures. But then it really isn't until only a few hundred years ago that we started to actually think, well, maybe there's some science behind this. And then only in the last 50 to 100 years have we really been able to make detailed scientific observations.
Tell me, when did you start becoming fascinated by all this sort of thing? I mean, were you intrigued as a child, or is this something that you grew into very much?
Oh, definitely. So this is something I've been interested as a kid for a long time. Maybe not the aurora so much, but space in general. I think looking at planets is really cool, and looking at the sun and how that drives things on Earth, I think, has really captured my imagination. And then as I went through my education and I did a degree in physics, I learned more about the aurora as part of a space physics module, and then it just ignited my desire to learn more about that, and that's why I've become a space physics researcher now.
Where did you see them first?
So I had seen them from the UK, but it wasn't a particularly amazing display. It was one of these where it's just sort of like a faint glow. Is it there? Is it not? And then I went for my birthday one year to Iceland, and it was amazing. It was a magical experience, a fantastic birthday present that I went out with my family, in fact, and minus 5-10 degrees below zero in just the night sky, and then boom, just there was the aurora, just overhead explosion of the lights and the movement that was going on, and that was my first real observation of the aurora. Obviously, I'd seen it in photos like a lot of people had before that.
A real emotional moment. I mean, people describe it being life-changing, don't they?
Definitely. I definitely believe that when it's a thing that once seen, it's never forgotten. It's an event in people's lives, and frequently the aurora come up in people's bucket list. So the things to do before they die is to go see the aurora, and it's always in the top 10 things to do. And I think we're quite fortunate here, especially if you live in Scotland. If you live in a remotish area, so away from the city lights, it's something you can do from home, as well as, before COVID, of course, but going to travel to places like Iceland or Norway or Canada to see them as well.
I've got a question here, but I think we've just maybe answered it. Where did you witness the most epic aurora activity?
Yeah, so that was definitely in Iceland. So I went there, and I went. My birthday is in November, and November's a good time. Anywhere from sort of November through till March, really, sort of late autumn to early spring is a good time to see the aurora, because you need these dark skies, so you need long nights. You also need clear skies, as I said, so you can't have clouds or anything like that. And so deepest of winter can sometimes get a bit clouded out. But Iceland was great. I went for 5 days and I saw the aurora every night, which was pretty fortunate for me. I know some people have been and they didn't see it at all, which would be quite upsetting. But it's all about making sure that you're going at the right time. You're looking at data and getting alerts as to when you might see the aurora.
Are there periods in our history when they were much more prevalent than they are now, or is that not really documented?
It is documented. So the sun's activity, as I mentioned, sort of waxes and wanes. So it goes from solar maximum to solar minimum. And that happens on a 12-year period. But the size of the maximum, so how strong that maximum is or how low that minimum is, changes on much larger timescales. And so over time, the sun has become much more active or much less active. And we're actually in a bit of a minimum now. So that the maximums aren't quite as high as they sometimes are, and the minimums are much lower than they sometimes are. And so that does change over time. And so being able to see the aurora is a privilege that we get to see. And sometimes it might be more visible, sometimes it might be slightly less visible.
Is climate change going to affect it at all?
Not that we know of. So climate change, generally we're talking much closer to the Earth, so lower atmosphere, whereas the aurora is much higher up in the atmosphere. And it's fundamentally just about this solar particles that have come from the sun, entered into our magnetosphere, and start raining down onto our onto our atmosphere. So really, it isn't affected by that. The only thing that could affect seeing the aurora, which could be sort of tenuously linked to climate change, is you need clear skies. And so if suddenly the weather patterns change significantly, then that might make it harder to see the aurora. But the aurora would still be happening. It's just you might not see them.
We've got some good questions coming in here. I've got one from David, which is, what is the current thinking about Steve and what causes it? And we were talking about that earlier, weren't we? That we had a Steve a couple of days ago in Shetland. Can you explain that, please?
Yeah, so Steve is for those that don't know, it's an atmospheric phenomenon that appears to be quite similar to the aurora. And it was first observed, well, it's been observed throughout history, but it's really only become well known by scientists in recent years. And that was thanks to citizen scientists. So that was people going out, hunting the aurora, trying to capture the aurora on camera. And they started noticing these purplish sort of streaks in the night sky that was quite detached away from the main auroral oval, so the main region where the aurora was being seen. And that was brought to the attention of scientists, and I was one of the members of that team who then analysed this. And we looked at data from satellites, and we looked at data from ground-based images, as well as the photographs that these citizen scientists had taken. And we were able to show that Steve wasn't part of the main aurora. It wasn't explained by our current understanding on various other sort of the dynamics and the various other little bits and bobs that go into the aurora. It couldn't be explained by that. And we were able to get in situ measurements, so actually sort of measure the magnetic field and the plasma temperature, the electron temperature in that region. And we were able to work out that it was this very fast flow of electrons in a certain region of the atmosphere, which we call the ionosphere. And that fast flow was generating its own mini aurora or aurora-like phenomenon. And so what we've spent the last few years doing is looking at what drives those conditions, how do they form, and what connection do they have to the whole system. But it's definitely an area of current research that we're still learning more about.
So it sort of leads into another question that's just come in, which is, are there any ways that the general public can get involved in research of the Northern Lights or be alerted as to when they might be more likely to occur? So I think you can tell us quite a lot about that, can't you? Yeah,
definitely. It's a great question, Dave. So for the first part, is there any way that you can get involved in research? Absolutely. As I've just mentioned, that it was thanks to the public that we actually started to learn more about this Steve phenomenon. And there's a few ways of doing it, but one of them is the AuroraSaurus project, which Polly mentioned I was part of a few years ago. And AuroraSaurus aims to collect sightings of the aurora and it can use those then as a data set for scientists to look at. So for example, when I worked on the project, I used people's observations of the aurora to determine at what latitude it could be seen from based on how strong the solar wind was, how fast that was blowing. And what we found out was that our computer models, our simulations, were actually a bit off, and that people were seeing it further equatorward or further south than we'd expected. And the thing that has really advanced this is that a lot of people now have really great cameras. They have these DSLR cameras that only 10 or so years ago really were not available to the public as a whole. But now they have these science quality cameras that can capture the aurora. They can capture very specific details. And it's now that scientists are realizing that this is a really rich data set to actually analyze and look at. And then the second part about being alerted to, well, yes, definitely. There are lots of Aurora alert services out there. I'm part of the AuroraWatch UK team, and we have magnetometers, which are scientific instruments that can measure the magnetic fields around the UK. And we use those to determine when the aurora is currently active and when we might be able to see it from the UK. But there are magnetometers across the globe that are detecting these changes in magnetic field, detecting how strong the aurora are, and you can sign up to alert services. So ours is AuroraWatch UK, but also if you have Twitter, then you can get alerts on Twitter or Facebook. You can get them there as well. And so when you get these alerts, then they tell you that activity is high, and you can go out and you can actually look for the aurora. But if you want to know in advance when you might see an aurora, then there's a whole bunch of data out there. So there's the Space Weather Prediction Center in the US, as well as we've got some here with the British Geological Survey and places like that. And they will try and estimate when you might see the aurora. We use computer models to say, based on some activity that we've seen on the sun, you may see an aurora in, say, 3 days' time or something like that. And then there are local groups on Facebook and on other social media platforms where people let each other know that an aurora might be seen, or I'm just seeing the aurora outside my house right now. And it's a fantastic way of sort of crowdsourcing that information. And so there's definitely a lot of resources available to you to see the aurora from the UK.
It's always great, except when you see your friends doing it and they're only about 5 miles away and they can see it and we're under a big blanket of cloud and we can't. Get in the car and drive madly, and it's quite funny because every light seems to be the aurora. You know, you get that you're just imagining it everywhere. It is so incredibly exciting. All the beliefs that were surrounded, you know, all the tribal people, they had extraordinary beliefs, didn't they, about what was going on?
I mean, yeah, definitely. And I think
some of those.
So in the sort of the North America, the tribal communities were quite spread out, and so they developed their own mythologies around the aurora. And because they weren't so much interlinked, they kept these like mythologies that were quite unique to each different tribe or each different sort of nation of people. And some of these were fascinating stories. You know, it was the souls of loved ones were dancing in the sky, and so people would go out and celebrate with the aurora because it would be connecting with their ancestors. Some of them, it was, as we've said, sort of messages from gods or omens to describe whether they were happy or whether they were sad or angry with the population. And in China, for example, yeah, they used to believe that the aurora was one of the celestial dragons that was in the night sky, and it was describing how these dragons were battling and the celestial battles that were going on. And I think it's fantastic that we've been able to sort of document the aurora through these millennia as we've gone through and looked at, you know, the history of these different tribes or these different civilizations to see really how connected they were with the natural world and with this majestic phenomenon.
I read somewhere that the Inuits thought that it was dead humans playing a ball game with a walrus skull. I mean, how did
That's very specific.
I mean, that's
I
just
mean, it's
bizarre.
it's fantastic what
I
what
love the
stories they come up
idea.
with. It's a way of just explaining something that they didn't know, and these stories are great. They add to the folklore behind the phenomenon.
I rather like the one too where they described it as being the spray from whale blow going into the atmosphere and causing that. I mean, it takes a lot of imagination, that, doesn't it?
It does, but if you don't have anything else to explain it, then you can come up with anything. I mean, I dread to think of the size of the whale that you would need to create a blow spray that high up into the atmosphere. But when you don't have any understanding of the connection there, then these stories become fantastic and magical, and it's something to really show interest in. I think it's fantastic.
They were connected to ravens and spirit guides, weren't they, as well, which was another aspect.
Yeah, definitely. So it's a very common theme. So it's either a connection with gods or it's the spirits, and I can totally see the spirit connection because, as I mentioned, the light coming through the sun, the light coming off the aurora can vary. So sometimes it can be quite bright and sometimes it can be more of like a wispy cloud. And so you can kind of get that ghost effect almost, rather than it being like this bright searchlight in the night sky. And in fact, I think I've got a picture here that shows the difference between a camera and by eye. I don't know if we can bring that one up. But so here, this is a photo that I actually took whilst I was in Iceland. And we've got these two parallel lines that are kind of converging, and they're the auroral arcs. And on the left, this is the photo that I took with the camera. And then on the right is kind of an impression of what I could see by eye. And just to note here that what you can see by eye will vary depending on each person. Each person's eyes are different. And so this is just a representation. But you can kind of see that it's kind of that wispy light, that color in the sky. And you can definitely see how that might be thought to be spirits or some connection to an otherworldly existence. And it's really interesting that a lot of people, when they see the aurora for themselves, they might think they're going to see that on the left. And sometimes you do. Sometimes it could be really bright and really strong, and you will see that by eye. But a lot of times you might see it more on the right. And that's just because the way that our eyes work, especially in darkness, they're more attuned to working in monochrome in darkness. So it's kind of, they work light or dark rather than color. Whereas a camera with its sensor can increase the exposure length of an aurora, for the capturing of the aurora. So they'll be able to really pick out that color. But yeah, certainly sometimes people can see pinks and greens really vividly, and it does come down to you and also how strong the aurora are.
I suppose too, nowadays with Photoshop, people oversaturate and really enhance their photographs too. So quite a lot of the things we might be looking at might not be 100% accurate. Would you agree with that? Do you think sometimes they're overblown, perhaps a wee bit?
I mean, I think it's subjective. I think ultimately it's art, and if it's someone's photo, then they're free to show that in the way that they want to. I think certainly they can be a little bit misleading sometimes if they're really overexposed or really the contrast has been boosted, then that isn't what you're going to see by your eyes. But that's more of a limitation of your eye rather than saying, well, you're photoshopping or faking the image. It's just that that's what's seen by camera versus what's seen by eye. So don't be disappointed if you hunt the aurora and you see something of like grey wispy clouds. That might actually be the aurora.
How does it compare to the Aurora Australis? And have you ever seen that?
I haven't, no. So the two phenomenon are essentially the same. It's the exact same physics that's occurring. It's just one's at the North Pole, so the borealis, the North Pole, and then Australis for the South Pole. We tend to think more about the Aurora Borealis for a couple of reasons. One is we are currently located in the Northern Hemisphere, but two is that the region in the Northern Hemisphere where people can see the aurora is much more populated than the region in the southern hemisphere where people could see the aurora. Because really, you can only see the aurora in the southern hemisphere from places like Antarctica, but New Zealand or the very southern tips of Australia. Whereas in the northern hemisphere, we get to see it from right across from the northern Europe, Canada, North America, and into the Russian sort of the Russian expanse there as well. So it's the same phenomenon, but it's seen a lot more in the northern hemisphere.
Right. I've got rather a good comment question here from Andy. I've heard that Galileo gave the phenomenon the name aurora, but I don't believe he ever left Italy. Do you have any idea what he would have understood about the aurora? Was it second-hand information? Would he have seen it that far south, albeit with less light pollution?
Yeah, that's a great question, Andy. So we can't know for sure, but what we believe is that, yes, they did occasionally see the aurora from Italy, from Greece, from France. And that would be during particular strong events, and also for the fact that the magnetic poles have moved a bit over time. And so it's likely that they did see it occasionally from the Mediterranean region. And they call it Aurora, which is the goddess of dawn, and that it came between night and day, which is quite an interesting idea, because obviously we see the aurora during the night, but that it is like the light of day. Okay, it's not quite as bright as that, but we're producing light in darkness. And so it's kind of this intermediate state between day and night. And so I don't think that they would have understood the principles behind the aurora. Certainly there was no evidence that there was that connection there. But it's whether they could perhaps understand that maybe there was some science behind it rather than just the gods, which would tend to be the prevailing view at that time.
Mm. Now, Isla has asked, what's the best camera setting to use to photograph the aurora if you're just using a standard DSLR? It's a difficult one.
So firstly, just to say, a standard DSLR is fantastic. That's really all you need. I've seen photos of the aurora. In fact, when I was in Iceland, I was able to take some with my phone as well. The biggest thing when it's with your phone is that you need to keep the camera stable. And so if you're holding a phone, actually you're not keeping it very stable at all, and you're going to start getting wiggles in the image. So the big thing with shooting with DSLRs is to ensure you've got a tripod, because what you're going to want to do is you're going to increase the exposure time, and you'll need to play about a bit with your camera, and depending on how strong the aurora is at the time, as to how long you want to expose the image for. But if you can change the exposure time, and if you can change the ISO levels, then that will help really reduce sort of the noise that you're seeing as well in the image. So it depends on the aurora, depends where you are in the world, but the best thing is definitely to have a tripod so that you can keep the camera still. You might even need to weight it down. If you're in Iceland somewhere and it's blowing a gale as you're out there and your tripod's shaking, then you'll need to keep that steady as well. And then really just start playing around, start adjusting with the exposure and the ISO.
I suppose people might also want to know, what would be a good app that you would recommend for them on their phones for following the aurora?
So yes, there are plenty of apps that you can download. I mean, I should plug the AuroraWatch UK app. That offers alerts, so you can get notifications on your phone when we offer when we produce a yellow alert or an amber alert or red alert. There's different levels that we produce, and that will tell you if the aurora is being particularly strong right now and from where in the UK you might see it. But there are other alert services and other Aurora apps as well. On one of the AuroraWatch apps, we have the ovation model, which is a computer model, a simulation of where we think the aurora is based on data that we're getting from satellites that are in between the sun and the earth. And they're recording that solar wind and how strong it is and how strong the magnetic field inside that solar wind is. And then they can issue you sort of predictions as to when you might see it. So if you're serious about hunting it, or you're going on holiday and you want to look, then always do a bit of digging around, find where you're going, find if you can get some local apps that will tell you what you can see the aurora. I went to as I say, I went to Iceland, and Iceland have got this web page that the Icelandic Bureau of Meteorology produce, and it tells you both the cloud locations and where that's blowing to based on the current wind, and tells you how strong the aurora is likely to be. And so you can sort of then pick out pockets of clear skies as to where you might try and race off to find it. And you can do the same here, as we've discussed. If you're a member of some Facebook groups, or if you follow the right people on Twitter, then they might be able to tell you where to go and where to find it and how much warning you might have.
It seems to me that the aurora has spawned a huge tourist industry up in Scandinavia, hasn't it?
It definitely has. I think it's one of Iceland's big things that they really focus on, is the aurora. Obviously, it's a beautiful country itself, but the aurora is a massive draw for them in terms of people going to visit, especially in those winter months where in Iceland you may only get sort of 4, 5, maybe 6 hours of daylight, and so you might struggle to do other things during the day, but that night experience of going out and hunting the aurora is a real draw. And it's even something that we're trying to capitalize on in parts of the UK too. So I know in the Shetland Islands that they're using that as a draw, because the Shetland Islands are a great place to go see the aurora from the UK, because they're located so far north. Even from the Scottish mainland, they're quite considerably far north of that too, and so they're a great place to go see it. But so are the other Scottish islands and the Scottish coast as well.
Have you spent a lot of time in the islands looking for it, or not yet?
So I've been to a few of the islands, but in summer, which is not great, because obviously one of the great draws of the summertime is that they have those long summer nights, and so we won't see the aurora then. But I have been to Shetland, and I have captured the aurora myself on a camera up there. Not quite to the same level as in Iceland, but I know that there are some webcams that are hosted up in Shetland, and on those webcams they actually point them north, they're facing north, and they're capturing the aurora when it happens, and it's fantastic to see them up there too.
Susan has just sent in a good question. Could it be seen on other planets?
That's a fantastic question, and the answer is yes, definitely, Susan. What we know is that any planet that has an atmosphere and a magnetic field will have an aurora, and basically the principle is the same. So this energy and these solar particles are coming off the sun, and they get blasted out into the solar system. Some of those will sometimes hit Earth, but sometimes it will go further out. They'll continue out into the solar system and interact with the other planets. And so I have colleagues at my research center where they are studying the planets on Jupiter or Saturn, and they use missions such as Cassini, one of the famous spacecraft missions that went around to Saturn. But then they also use the Hubble Space Telescope to then look at the aurora on these planets as well. And so whilst the colors that we see and the compositions of the atmospheres are different, they're still producing aurora. And in fact, it's been hypothesized, and there's no reason why it shouldn't happen, but that there are auroras on planets outside of our solar system too. And so making those first observations of those would be pretty tricky, especially with using visible light, but it's almost certain that there would be aurora on many planets across the galaxy and universe.
Have you got a goal now of things you really want to find out that are very difficult to discover to do with the aurora?
Yeah, there's a whole active research field, and there are people working across the globe on auroral dynamics and understanding how the aurora changes and responds to various different things. It might seem as though we know a lot about the aurora. We certainly know on the large scale picture what happens, but on the much finer scales and much finer details, it can be very difficult to pin these things down. And the hardest thing is quite often to actually have observations of the whole aurora. So it's quite easy to take photos from the ground, but then clouds can be an issue, and that can make things difficult. So then we have to rely on satellites, but satellites are expensive, and so we can only send up you know, a few, even if we say 10 or 20 satellites, it's really only a few satellites up there. And those that can look down with cameras and actually capture the whole aurora and see what's going on is quite few. And so really we're looking into that dynamics and understanding that. But I think one of the most amazing things with, like, for example, the Steve discovery is just showing that things can pop up that we didn't even know were there. And so we might think we know an awful lot about it, and then just something appears that, well, that doesn't factor into what we know. So, and then we go away and we study that, and then we learn more about that, and then how that links into everything in the wider system.
Do you think it also highlights the fact that citizen science is really increasingly important, actually?
I think so. I mean, I'm a great proponent of citizen science, and it's being used widely and successfully in a whole range of different science disciplines and fields. And I really think it's something that can be used more in space physics generally. The difficulty we've had, of course, is that it's not reasonable to expect that Joe Bloggs can send a spacecraft mission up into, you know, go study Venus or something. You know, these are multi-billion-dollar missions that really can only happen with international cooperations between, you know, NASA and ESA, the European Space Agency, and other space agencies across the globe. But what citizen scientists can do is they can look at the data that's being provided by those missions. And so, for example, there's citizen science projects like Zooniverse that host lots of different individual projects, and you might be able to go look at photographs taken by Hubble of planetary disks or things like that, and you can then contribute that data, you can process that data and help scientists learn more. Or, as I've mentioned with AuroraSaurus, you can take photos of the aurora and report those to scientists who can then do some studies on them as well.
You've obviously got a great mission to explain it to other people too, because you do that incredibly well. You don't blind us with too much science. What is it actually that intrigues you most about the whole thing? Is there any way you could describe that?
I think it's the intriguing thing for me is understanding our place in the universe. And I don't necessarily mean from a theological point of view or a scientific point of view. It's kind of a mix of everything. When you look at us on Earth, and we are just this tiny fragment, this tiny speck on Earth, and the time that we've been around on Earth is just this tiny little tick of a second that we've been here. The aurora have always been there. They always will be there as long as we have an atmosphere and we have the sun. And the looking from the pictures like the ISS from the space station, looking down at the Earth and seeing our place on there, but then seeing how we're connected to the sun because the sun is driving these events that we're seeing on the surface, and just that whole interconnectivity and understanding where we are and what's our place in the universe. And it falls from that, really. I think that's, for me, that's a massive engagement.
I think that's brilliantly put. I must admit, I really have enjoyed chatting to you, and I could chat to you for hours. Just so much. Is there a good book that people could, I know you haven't got a book, a good book that you would recommend for people on the aurora that's sort of easy to understand and maybe relays a bit of this?
Yeah, so there are plenty of websites where people have documented blogs and things of hunting the aurora, and a colleague of mine, Melanie Woodridge, I know, has a book about the aurora and the stories that of local people that they've learned over the ages to associate with the aurora. And so that's a one to look out for as well, I think.
Great, thank you. And I do apologize for that phone ringing. I thought everything was all switched off here. Anyway, thank you so much, Nathan. That was absolutely spectacular. Really enjoyed it. And thank you for coming to Wigton Big Bang event and giving us such a fascinating chat. Thank you.
Thank you, Polly.
Okay, bye-bye.